The other one feels the effects, and there's plenty of potential for confusion, so I want to go through it slowly, starting with the effect side. So what I'm going to have is a region of space where I've been told that the properties of this space are that it's 9 volts over here and it's 3 volts over here. Why is that? Who cares right now? We're on the effects side. We don't care what caused that voltage. We're just talking about, we know that the space has these properties. And then into that space, we put in this object. It's a positive charge, specifically 1 coulomb, and it had a mass of 1 kilogram. And I put it down at both of those locations, and I calculated how much potential energy it had. Well, 9 volts means 9 joules available per coulomb, and I just put 1 coulomb there, so I got 9 joules. So when someone's handing you the voltage, they're handing you a lot of information. All you have to do is multiply by the charge you decide to put there, and they'll tell you how much energy is stored in it. So that charge stores 9 joules here and 3 joules here. I dropped it down in both places just to get a feel for how much potential energy was in each place. And then, of course, once I realized that it has more potential energy on the left and less potential energy on the right, I realized that this charge would spontaneously go from left to right, but not the other way around, because things like to go to lower potential energy. So all systems prefer to seek lower potential energy. Why does a ball fall down? Yes, the force of gravity is down, but how do we explain it with energy? Well, a ball falls down to get to lower stored energy. Okay? So this thing will fall to lower voltage. And in fact, that's one of the things I want to write here. I want to write that positive charges seek lower voltage. Okay? So a positive charge fell into a lower voltage region to get to a lower potential energy. Now we can turn this into a good old energy conservation problem. We can say that not only did we release it here where it has potential energy of 9 joules, but we also released it from rest. So it has 0 kinetic energy to start with. So we add these two up, and the mechanical energy overall is 9 joules. And of course, in the absence of friction or some other weird energy input, that energy better still be there at the end. So I copy that over here. I got to find my overall energy still here. Well, over here, I'm down to 3 joules, so the energy must have been converted into kinetic. So I am able to reason here that it's 6 joules. So it still has the same amount of mechanical energy, it's just differently manifested in the ratio of kinetic versus potential energy. And of course, I can set that equal to good old 1/2 mv squared, where v is the speed. And I think last time I gave it to you as square root of 12, but I think I managed to find in my notes the square root of 12 is roughly 3.5. So it arrives upon its final destination going about 3.5 meters per second. Basically, you can think of it as, projectiles like to fall down, while positive charges like to fall into lower voltage. And they'll gain speed while doing so. Kind of think of it like this, right? It's like if you had one of these problems from Physics 1 where you had a roller coaster and someone's handing you what are the two heights, right? H initial and H final. So the only thing that you need to supply, of course, aside from which planet you're on, which I guess I'll put in here, G, you need to supply what mass you're going to choose to put at those heights, right? So you have your roller coaster car that has a certain mass m, right? So that's like what I'm doing here, right? I'm taking a property of the location, multiplying it by what I put there, and I get the potential energy. So this is good old mgh, right? You guys remember this? Okay, so this is the initial gravitational potential energy, and this is the final. So when someone hands you two voltage values, if you just multiply in what charge you're going to use, you basically have what's the energy at the end and energy at the beginning. And then lots of things can happen in between. Maybe it looks like this. Maybe it looks like this. that would take, by the way, longer time, because you'd spend most of your time going kind of slow and just speed up at the very end. If you had a steep downhill and then cruised across the bottom flats there going very fast, that would take a lot of time, or very little time, rather. So there's lots of different ways to connect these. Constant acceleration is not necessary. And of course, the one thing that you give up is being able to find the time. Those things would all take different amounts of time. But all of them, you would end up trading the same amount of kinetic energy, potential energy into kinetic energy, right? So no matter how you got there, you'll have the same final speed at the end. So you have the same potential energy loss regardless, which translates into kinetic energy gain. So you have the same final speed. So you have this mass here, you let it go down in various ways, and when it gets here, you can calculate the final speed. That's essentially the flavor of what we're doing. It's just easy to remember with gravity that everything likes to go downward. Here we're going to have different rules for positive and negative charges, but for right now, remember that positive charges like to seek lower voltage. That's what they fall, quote unquote, fall down into lower voltage. Okay? So lots of different ways that this could happen. The only thing, of course, that couldn't happen is if you release it here from rest, right? Let's say release it here from rest, it could not go up there, right? It wouldn't have enough energy to do that. It doesn't have any kinetic energy to trade to going to higher potential energy than it has to start with, right? So that's the same thing here. I can't have 1,000,000 volts in between. It would never make it over that hump. Does that make sense? Okay. So the next thing I want to do is let's make it a negative charge. So same region of space. You might want to sketch it down again. Same plus 9 volts and plus 3 volts. And everything's going to be the same except I'm going to change my charge to be negative. This is something we did not have to contend with whatsoever in Physics 1, where everything was positive, right? So in Physics 1, kinetic energy was 1/2 mv squared. That's positive. V is already speed, that's already positive, but squared is definitely positive, times mass, which is positive, so kinetic energy is positive. And potential energy was mgh. Mass is positive, g is positive. And the height, well, we went to great lengths to not have to deal with negative heights because we always tended to set h equals 0 at the lowest height of interest. And so we tended to kind of set it at the floor of whatever the problem was. So we were either at the floor or higher than that. So that meant that this was always positive or 0 at the worst. We never had any negative heights to deal with. So this is going to require us to stretch our ideas about potential energy a little bit more. So let's go ahead and drop this at both locations. I'm going to in turn place it at each one. Those aren't two charges. I'm going to in turn put it in each place. Let's follow the equation. We'll follow it to the letter of the law exactly there. Let's go ahead and, for instance, say, well, we have a -1 Coulomb charge, and we're putting it where there's plus 9 volts. Remember, a volt is a joule per coulomb. So what that means is it has -9 joules of potential energy. So that's our first negative value. What's that about? We'll find out. So the potential energy of this charge placed here is -9 joules. And over here, as you can probably see, it's going to be -3 joules. So these values are negative. So we have to keep straight what that means. Now, I know that for most of physics 1, I drilled you into thinking about negatives and positives as being applied to vector components, right? Positive is when you point along the positive axis, and negatives when you point the other way. Yes? Okay. And when I asked you which is bigger, you're basically ignoring that. So if I ask you, for instance, to compare -9 meters per second and -3 meters per second, you tell me -9 meters per second is bigger, right? Because that is 9 meters per second to the left, and that's faster than 3 meters per second to the left. But these are not vectors. These are negative numbers, negative scalars. We had those, by the way, in physics 1 as well, most notably with work. So work could be positive or negative, and it had nothing to do with right or left. Well, this is where we have an energy value itself, which is for the first time positive or negative. So let's talk about that. I'm going to put over here what I call the potential energy spectrum. And I'm going to basically put a number line here so that I can mark off values, and I'm going to orient it vertically. And the only reason I want to orient it vertically is because that way we can kind of visualize it like gravity, right? With gravity, something has lower potential energy closer to the floor and higher above, right? When you're toward the ceiling. So I'm orienting it vertically so you remember that the higher up you are, the higher potential energy you have, the lower you are, the lower it is, okay? So this, toward the top of the page, is higher potential energy, okay? And what we said was that all systems prefer to go to lower potential energy. Well, why is that? The force always points that way. So again, why does a ball fall down? Because the force of gravity pulls down. What's the answer in the energy perspective? Well, going toward the floor is going to get energy out of storage. It goes into kinetic, right? So that is the natural thing that systems want to go this way. Systems want to lower their potential energy. So they want to go lower. Now, I don't mean to say that it's impossible to ever go to higher potential energy. We already know that's possible, right? We throw a ball up in the air. So a ball thrown up into the air goes to higher potential energy first and then comes back down. So yes, it can go that way, but of course, that's only because you gave it an initial toss the wrong way. So it takes a bit for the gravity to chew off that initial throw in the wrong direction and have it come back down the way it wants to go. So it's perfectly fine to start off going this way, but you will eventually want the system will want to go to lower potential energy, okay? So basically think of this as if you have any two states of the system, one which is higher on this number line and one of which is lower, it'll always want to go from higher to lower in a natural tendency and never the other way around. So our first example, it was pretty obvious. We had a +9 joules and a +3 joules. And so it was very obvious that the system wanted to go from +9 to +3. That's the one that I just erased off the board. Now that these numbers are negative, we have to be a little bit more careful. So let's put those on the number line. We have -3 and -9. So which one is lower? -9. So the natural tendency of this system would be to go from -3 to -9. So if I were to test this negative charge out at both of these places, what I realize is that the system would if I released it here, it would spontaneously fall over there, not the other way around. So I'm going to call this the initial point, and I'm going to let it go over here. and this will be my final point. So I want to point out that it's exactly the same spatial region with the same voltage values that I had before, but now because I put a negative charge into that region instead of a positive, the natural tendency of that negative charges do go the other way. And again, that shouldn't be surprising, because whatever the positive charge wants to do, often the negative wants to do the opposite, right? So what we actually find is that minus charges seek a higher voltage. The voltage value that it's going to is going from 3 volts to 9 volts. But both of these seek lower potential energy. So everybody seeks lower potential energy. It's just how you achieve that is different. Positive charges fall into lower voltage, while negative charges fall into higher voltage. And as they fall, they get rid of their potential energy and convert it to kinetic. Let me give you an analogy, okay? Everybody seeks lower potential energy. What's an analogy for real life? Everybody wants to be happy, okay? Let's just take that as an assumption, okay? Everybody wants to be happy, okay? So, if everyone has that same goal, different people try to achieve that goal in many different ways, sometimes seemingly completely opposite. So, positive charges seek lower voltage. That's like someone says, I would be happy if only I could get rid of all my worldly possessions and just go live on the beach, okay? So I'm getting rid of stuff to be happy. And then there are other people who say, if I only had $1 billion, then I'd be happy, right? So some people want to get rid of stuff, some people want to gain stuff, but all under the same service of the same goal. So that's the difference. Everybody wants to seek lower potential energy, but they do that by going completely opposite ways. Positive charges seek lower voltage, minus charges seek higher voltage. Now this is a great opportunity for me to justify to you why I say voltage all the time instead of, which is a nickname, instead of electric potential. Because if I substitute in for voltage the fancy name electric potential, I can say things like negative charges seek higher electric potential to get to lower electric potential energy, okay? I'll say that again. It sounds like I just contradicted myself in that sentence. Negative charges seek higher electric potential to get to lower electric potential energy, right? That's the problem with electric potential voltage and electric potential energy sounding so similar, okay? So electric potential energy are very different things, and you can simultaneously go to higher value for one and lower value for the other. So remember, if you hear electric potential, you're waiting. If you hear energy, oh, okay, that's PE. If you hear crickets, electric potential with nothing after it is voltage, okay? In fact, I should point out that in this formula, the lowest possible value on this number line that you could get to is down here. It's minus infinity. That is the lowest value on a number line. And the way that a negative charge would get to that coveted value was actually by going to the highest voltage value possible. It's that extra minus sign that throws in the wrench into the works. This is the lowest value, and that's the highest value. So a minus charge would be psyched if it could get to the highest voltage possible. It's like infinity money, okay, to be the lowest potential energy. Okay, so it's that extra minus sign that flips things around. So negative potential energy. Negative infinity is the lowest you can do. If you can get that in that system, that's the best. Now, it's not available in every system, as we'll see, but if you can get whatever's the lowest value you can get to on this number line, that is what the system wants to go toward. The highest value is plus infinity, and that's the worst. No system wants that. All systems want to go to lower potential energy. May not be able to get to minus infinity. That's the very best possible. But whatever is the lowest that they can move down the scale, that's what they're going to do. Now, 0, we're so accustomed to thinking of 0 as the end of the line, but 0 is nothing special. It was something special for physics 1 only because we set h equals 0 at the lowest height of interest, which meant that our potential energy was 0 there. Okay? But that was simply to save you from having to contemplate negative potential energies in physics 1. We've got to save some fun for physics 2. So h equals 0, or potential energy being 0, is nothing significant. That's like saying if you have an origin, x equals 0, I'm only allowed to move to one side. Well, I can easily walk past x equals 0 to negative x values. What's wrong with that? The only reason you couldn't walk to negative x values is if you set x equals 0 right at the wall. So you can only walk to one side of the wall, but when you try to walk to the other side of x equals 0, you hit the wall. It's the same thing here. I'll give you an example. Let's say in physics 1, I gave you a problem where you threw a ball up in the air. It went up, it came down, and you're like, okay, that's my problem. I'm going to set my h equals 0 at the lowest height of interest. That's my potential energy is 0 here. And then someone told you, oh, I'm sorry, I didn't tell you. I know you've already set up your 0, but there's a hole here. And it's going to keep falling. Okay, well, if it falls into the hole, as it falls in there, it's going to keep speeding up, right? So it's going to keep increasing its kinetic energy. Well, where does that kinetic energy come from? You can't get more kinetic energy without doing what to your potential energy? Decreasing it, right? You got to get that energy from somewhere. How are you going to decrease it if you're at 0 already? Well, you just go to negative values, right? So here we have negative heights, and we have negative potential energies, and negatives are lower than 0. So potential energy being 0, it doesn't mean that you've wrung every last drop of potential energy you have. 0 is nothing meaningful in many systems. You just keep right on falling into the hole. You go from 0 potential energy to negative potential energies, and negatives are even lower. So you have the ability, even at potential energy of 0, to keep lowering your value. And of course, if you lower your potential energy, you can get it out as kinetic. Okay? So even in physics 1, we could have had negative potential energies if we just didn't always set the 0 at the lowest height of interest. Okay? Now in physics 2, we have to acknowledge negative potential energies. It's just essential. So remember to think of this here, and always think and mark off your values of potential energy, whether they're positive, negative, 0, whatever, and always think that the higher value is where the system wants to get away from. It wants to get to the lowest value available in the system. So let's go ahead and go over here. Back to my original problem. I've calculated the potential energies at each place. I've decided that negative 9 joules is lower than negative 3. And let me give you a little bit of a flavor. Let's say, for instance, we drop it at this point at rest. So the kinetic energy is 0. So this is just dropped at rest. You don't have to, you can throw it, but just for sake of simplicity. So here I would add these two to get the overall mechanical energy. That's minus 3. So my overall mechanical energy of the system is minus 3 joules. And of course, barring any kind of friction or anything like that, we got to see it all the way over here. So we lost potential energy. We know it when it's kinetic. So we can reason here, what would be the amount in kinetic energy? 6 joules. Now this still came out positive. And I want to point that out. That's very important because while potential energy can be plus 0 or minus, kinetic energy has to be positive always. There is no option for kinetic energy itself to be negative. look at the equation, right? We haven't changed the equation for that. We've changed the formula for potential energy, but kinetic energy is still 1/2 mv squared. So how is that ever going to be negative? So if you wind up in a situation where you find your kinetic energy is like -6 joules, you did something wrong. Okay, that's impossible. The kinetic energy has to be positive always. And it is in this case. We have these other minus signs flying around, but the kinetic energy came out to be positive as always. And of course, I gave you the mass, same as before. So I would just set 1/2 mv final equal to 6 joules. I'd solve for the speed, and that's the same as before. Basically the same example I already did earlier today, with the exception that it's a negative charge instead of positive. Okay? So that right there is the general gist of solving these. You notice that it's good old Ke plus Pe conservation, but the potential energies may be negative. The kinetic energies can never be, but the potential energies can. Okay? Are there any questions so far?